Hello, welcome back to Solid State Physics lectures. We know that the materials can be classified into metals, insulators and semiconductors based on the resistivity or the carrier concentration in the material. Okay. So the resistivity, if the resistivity is very high, the materials are termed as insulators. If the if the resistivity is very low, then such materials are called metals or conductors. Okay, so the intermediate resistivity materials are called semiconductors. From today, we are going to discuss the semiconductor crystals. Okay, so the semiconductor crystals, the resistivity lie between 10 raised to minus 4 ohm meter to 10 raised to 7 ohm meter. Okay, so if the generally if it is less than 10 raised to minus 4 ohm meter, they are termed as metals, and if the resistivity is greater than 10 raised to ohm meter, up to 10 raised to 13 ohm meter, they are termed as insulators. Okay. Now, at absolute zero, the perfect crystals of semiconductors are almost they are insulators. Okay. So that means intrinsic semiconductors at 0 Kelvin are normally insulators. Okay. Now let us talk about some compound semiconductors first. Okay. So compound semiconductors are having a chemical formula of the form AB. If A is trivalent and B is pentavalent, such semiconductors are called 3,5 semiconductors. Similarly, if A is divalent and B is hexavalent, okay, A is divalent and B hexavalent, then they are called 2,6 semiconductors. Okay. Examples for these 3,5 semiconductors are gallium arsenide, indium, antimonide. These 2,6 semiconductors examples are zinc sulfide, cadmium sulfide, etc. Okay. So there are 4,4 semiconductors. Okay. Example is silicon SiC, silicon carbide. Okay. So these are the compound semiconductors. So these are pure semiconductors. Next we can talk about the band gap. So materials can be classified in terms of band gap as well. So what is the band gap? Band gap is the energy between the lowest energy of the conduction band. This is conduction band, and there is valence band of electrons, electron energy. So this is valence band. Okay, so the uppermost energy of the valence band and the lowermost energy of the conduction band, this difference is called energy gap. Okay, EG. So based on this energy gap also we can classify the materials into metals, semiconductors and insulators. Okay. Now pure semiconductors are called as intrinsic semiconductors, that we know. Intrinsic semiconductors means pure semiconductors. So at T equal to 0 Kelvin, the intrinsic semiconductors, the conduction band is completely empty. At T equal to 0 Kelvin, this is completely, here the electrons are occupied, but here completely empty. Okay, at T equal to 0 Kelvin. So they behave like insulators. Now, as the temperature increases, when temperature increases, electrons will be excited from valence band to conduction band. As temperature increases, electrons are excited from valence band to conduction band, leaving a hole in the valence band. So a hole is there in the valence band and electron goes to the conduction band. So this both electron and holes contribute to the conductivity. So there will be two carriers from one excitation. Okay, so they contribute to the conductivity of semiconductors. Okay, so at T equal to 0 Kelvin, the conduction band is empty, therefore the material is insulated. As temperature increases from 0 Kelvin, as the temperature increases, the electrons are excited, more and more electrons excited, leaving corresponding holes in the valence band. And both these holes in the valence band and electrons in the conduction band contribute to the conductivity of the material. The conductivity of the intrinsic semiconductor depends on the ratio Eg by kT. Okay. If this ratio is low, the conductivity is large. Okay. So that means the resistivity is low. If this ratio is low, resistivity is low. Okay. Resistivity is low means when temperature increases, as T increases, the resistivity of the semiconductor decreases. Okay, so that means the conductivity increases. As temperature increases, conductivity, of course, more and more electrons will be excited to the conduction band. Okay, so more electron hole pairs created. Okay, so as temperature increases, the conductivity increases, but resistivity decreases because they are reciprocal to each other. Therefore, these semiconductors, pure semiconductors, they have negative temperature coefficient. Okay, negative temperature coefficients. Okay. Next, we talk about the direct and the indirect band gap. So the semiconductor crystals can be classified into two types based on their band gap. Some semiconductors have direct band gap and others have indirect band gap. So what are the difference between these? If we plot the energy versus K diagram in this axis, the wave vector K, okay, in this axis energy, okay, so we can plot the conduction band and valence band here. That if this is the energy of the energy level diagram of the valence band and this is the conduction band. Okay, so the lowermost energy conduction of the conduction band is called conduction band edge. So this is the conduction band edge, and the uppermost energy of this valence band is called valence band edge. Okay, so this is valence band edge. This is the conduction band edge. The band gaps of materials can be measured by optical absorption. That means if a light photon is sent to a material, it may absorb the material if the band gap, if the energy of the photon is greater than the band gap energy. If omega g is the, if omega g is the threshold frequency for absorption of photons, then the corresponding band gap energy is called is equal to Eg is equal to h cross omega g. Okay, if the frequency of the photon is greater than this frequency, it will be absorbed. Okay, so the electrons from the valence band goes to the conduction band. Okay, if a photon of this energy is absorbed by a crystal and an electron hole pair is created, such crystals have a direct band gap. Okay. Okay. So they have a direct band gap, and this conduction band and valence band edges happens to be at the same wave vector k. Okay, so this edge, both edge, this is the valence band, sorry, conduction band edge, and this is the valence band edge. So there happens to be, they are at the same wave vector k. Then such band gap is called direct band gap. Okay, if the band gap is direct, then an absorption of photons causes a electron hole pair creation. Okay, but in the case of indirect band gap, the conduction band and in indirect band gap, the energy level diagram, energy k diagram, ek diagram of the conduction band and valence band is like this. So here this is the valence band, and here the conduction band edge comes here. Okay, so this is the minimum energy. Okay, so this is the minimum energy difference between the valence band and conduction band edges. Okay, so this is equal to Eg. But if a photon of this energy is absorbed, then it will not create a hole electron hole pair, but it is associated with the change in momentum as well. Okay, so there is a change in momentum. So the momentum of this valence band is this k1, and here the momentum of this conduction band edges corresponding to the conduction band edges is k2, and there is a difference in momentum. Okay, delta k. Okay, so we can write the equation of momentum like this. K is the photon energy is given by K is equal to Kc plus capital K. Where capital K is the photon energy, Kc is the capital K is the photon wave vector, Kc is the wave vector corresponding to the electron photon separation. Okay, and the threshold energy of the photon is given by H cross omega is equal to the minimum separation Eg between the conduction band and valence band edges plus H cross capital omega. So here a phonon also created. So there are a photon, electron, and a phonon involved in this process. So this is a three entity process. Okay. In some cases, there will be, or this can be also written as, sometimes it will be H cross omega is equal to Eg minus H cross capital omega. In this case, a phonon in addition to photon also absorbed. Okay. So in this case of the indirect transition. Okay. So this is here phonon created. In here phonon is absorbed during the transition. Okay, so it involves three entities because therefore this indirect transition are at a much slower rate than direct transition. So direct transition occur at a much faster rate, whereas the indirect transition occur at a slower rate. Therefore, indirect materials are not used for making optical devices. Okay. So the example for direct transition metals are direct transition or direct band gap materials are gallium arsenide, indium antimonide. Okay. But this indirect band gap material example is silicon. So silicon is not used for making optical devices because the transition or the electron hole pair created at a much slower rate in the case of indirect transition. Okay. So the difference between these two is from the figure, it is very clear. The energy diagram, it is very clear that the valence band and conduction band edges occur at same wavelength. Okay, whereas in the case of indirect band gap materials, the valence band and conduction band edges occur at different. They are separated by large wavelength. Okay. So this is about the direct and indirect. So you remember that for making LEDs, photodiodes, indirect band gap materials are not used. Okay, so silicon is a semiconductor, but silicon is not used for making LEDs, photodiodes, etc.